Hello and welcome again in this advanced conduction lecture series. So we were doing the, we were solving the various cases, the thermal conduction equation, the heat equation, and uh, we will just proceed with that only in today's lecture also. That is, we will take up some arbitrary case and we will solve that. Now, you may be thinking that why arbitrary case? There are some special cases that we have studied in during our B.Tech course. I mean, for the guys who have done the basic heat transfer course during their B.Tech or BE. Now, let me tell you that approach where the GATE coaching center faculties tell you that if I have a given situation, any standard situation, the situations which generally come in GATE exams, okay, like if you have a slab like this, and if you have this wall temperature as T1 and this wall temperature as T2, and you have uniform wall heat generation, then this will be the equation of the temperature profile. This is the position of the maximum temperature and all. So they expect you to remember that, that is so that if that particular equation or that particular situation comes in the exam, you can answer that just by remembering the formula. But there can be cases that you can forget a plus or minus sign, a square or cube in the, in the pressure of examination, right? So the ideal scenario is not only for GATE exam to, I mean for for the scenario of to be a good mechanical engineer, you have to be in a position that you know the governing equation, and even if you don't recall the governing equation, you can derive the governing equation just by seeing your notes. You can recall all the fundamentals and you can derive the governing equation. Now you have the governing equation, and according to the problem you can modify the governing equation, and you can write the boundary conditions according to the given problem, and you should be able to solve that problem from scratch. If you can do that, then you can solve any problem in any examination. Okay, so build that kind of a mindset. I am not telling that don't mug up or don't memorize any of the formula for GATE, because in GATE you have to memorize formula. I agree with that, but first first be convinced that you are okay with all the fundamentals of that particular formula, that how that formula came. If you are asked to derive the formula in an interview board, in a blackboard, then you should be able to do that. Okay, so remembering that or keeping that in mind, here in this course I am telling you that you have the governing equation. Then other than the problems that I will be doing in this class, you take any arbitrary problem. Obviously not all the problems will have analytical solution, but you take any, I'm telling you, you take any one dimensional with or without heat generation steady problem, and you play with the varying boundary conditions. Okay, this you can do uh, up till now. Whatever I have taught you, with that you can do this, right? So you should be able to do that. So in this lecture, at first I will take some another situation in which I will be having heat generation. Okay, so let us proceed with that. So today I guess is lecture 7 or 8. I actually do not recall that what is the lecture number. Okay, maybe lecture 7. No, today is lecture 8. Okay, so this is lecture 8. So let us consider a scenario like this, that is I have a block, okay, and I am only considering the heat transfer in x direction, that is this. So this is my x direction. In y and z direction I am not considering the heat transfer. Okay, and I have uniform volumetric heat generation rate q triple prime. Okay, that is given as a constant. So this is constant throughout the volume. Keep in mind that there is no compulsion that q triple prime should be a constant. Okay, it can vary with position. Okay, now also it can vary with time according to the practical scenarios. Okay, so can you take up some practical examples of heat generation? Can you think of some practical examples of heat generation? So just write those in the comment box. Okay, at least three you write the practical scenarios of heat generation. uh, I mean, where can you see those things? So this is the x, and you have the boundary conditions. Like here you have T ambient in this phase as T1 and H1. Okay, that is given, and here T ambient is T2 and which is greater than T1 and H2. Okay, and one dimensional heat transfer that is given. So still I am just writing that. Okay, one dimensional heat transfer, and the dimension is x direction. Okay, okay, so the first step is what I told you, that the first step is to write the governing equation, right? So what is the governing equation? Rho Cv del T plus divergence of Q, right, minus Q triple prime is equal to 0. Okay, so another condition is that this is steady. Okay, steady heat transfer. We want to find the steady temperature profile. So if it is steady, then this is gone, right? And this we already know that this we can write as del qx del x, and all the other two terms, that is del qy del y and del qz del z, is identically 0 because qy equal to qz equal to 0, because there is no heat transfer in y and z direction according to the given problem. And this is, we know that minus k del 2t del x2 according to the Fourier's law of heat conduction, right? That means the equation boils down to, and this actually I can write as ordinary derivative instead of the partial derivative. The reason is very obvious, that is, it is a one dimensional problem. So this is the ultimate governing equation. Okay, this is the final governing equation. Now what will be the boundary condition? Now at this moment I encourage you to pause the video and write the boundary conditions by yourself, and after that you just match those results with that of me. Okay, so okay, so here let me just mention the length. So this length can be any, so as we have taken our origin at the middle of the plate, so I will take this is 2L, and this through the middle line okay, through this middle line is L and this is L. So this phase is essentially x equal to minus L and this is x equal to plus L, correct? Okay, so then boundary conditions. So first I have written the governing equation, then I have to write the boundary conditions. Okay. So firstly, at x equal to minus L, what is the thing? So first you have to decide that in which direction you will assume your heat to flow. So generally, I mean, uh, see here the T2 is greater than T1. So we can actually surely say that the heat will flow from this to this, that is in the negative x direction. So in this phase we will show the heat flow direction like this, and in this phase it will be like this. Okay. So you see at x equal to L and at x equal to minus L, at both the phases the heat flow direction is at negative x direction. So I told you that how to write the negative x direction heat transfer. So the in the positive x direction the heat flux is given by minus k dt dx. So in the negative x direction it will be this. So this will be equal to h into T wall minus T, right? For x equal to minus L, heat is flowing from this to this. That means it will be T wall here minus T1 here. Okay, it will be T wall minus T1, because as I have assumed that my heat will flow from the block to the ambient, therefore my wall temperature must be greater than the ambient temperature. Keeping that in mind, here I will write T at x equal to minus L, or you can directly write, for the sake of simplicity of writing, T at minus L, okay, minus T1. So mind it that here this is given, okay, so this was given as H1, okay, so here this is given, this is also given, okay. Okay, and this is what? This is, I have to find this delta T delta x, and obviously I should not write del anymore, I should write d, okay, at x equal to minus L. So if I write it in a compact way, then this at x equal to minus L is equal to h1 T at minus L minus T1, okay. This is at x equal to minus L. Now at x equal to L, similarly, because the direction of heat transfer is still in the negative x direction, then it will be at x equal to L is equal to H2, but here now you see that the heat is flowing from the ambient to the block. Therefore, I know that my T2 is greater than this T wall, and therefore I have to write here T2 minus T at L. Clear? This is my second boundary condition. Now your homework is to write the boundary condition assuming the second convention. Which convention? That is, the heat flowing into the block or into the system is considered as positive. If that is so, then here this heat flow is positive, right? This heat flow, this heat is going from ambient to the block. That means this heat flow is positive, but this heat flow is negative, right? So accordingly you write the boundary condition maintaining that convention, and you see if you are getting these equations or not. So I can write this as finally k dt dx at L is equal to H2 T2 minus T at L, correct? Okay. So just let me name these equations or number this equation. This is 1, this is 2, and this is 3, okay. Okay, so now we have to solve it. So let us write the equation 1 again, that is k d2t dx2 plus q triple prime is equal to 0, and remember that q triple prime is a constant. So this I can write as q triple prime by k, right? So then I can solve it like dt dx is equal to minus q triple prime by k into x, and again I can write it okay, there will be a constant of integration, I write it as c1. So this will be x square by 2 plus c1x plus c2. Okay, okay. So now if I have to put these things, so taking the first equation, so let me copy this equation here. Okay, so this is the first boundary condition, equation 2. Now from here you put x equal to minus L in this equation, because I have to find this one dt dx at x equal to minus L. So if I write that k into what, minus q triple dot by k into minus L plus c1 is equal to h1 t of minus L, that is unknown, but I have to write this t of minus L from this equation, right? In this equation you put x equal to minus L, so then we will get minus q triple prime by k and L square by 2 minus c1L plus c2, okay, and minus t1. So this will be the final equation. If I write in a more compact way, then plus q triple prime into L plus ck1 c1k is equal to h1, right? H1 that is a very untidy equation actually, minus h1 q triple prime by k L square by 2 minus c1 h1L plus c2 h1 minus h1 t1, right? So this is the equation where we get the unknowns here. See, in this equation unknowns are c1 and c2 only, all the other things you know, okay. Similarly, if you write the same, the second equation here, so I will copy this. Okay, so this is the second equation, this equation 3, right? So here again I will put k into now dt dx at x equal to L. So you put here at x equal to L, so that will be k into minus q triple prime by k into L plus c1, right? Yes, is equal to h2. Now t2 is given minus t at L, so you put here x equal to L here, so that will be minus, okay. So let me put a second bracket here, so it will be minus q triple prime by k L square by 2 plus c1L plus c2, this will be the equation, right? Just check the algebraic calculations, in case I have made any mistake you just rectify it and put that in the comment box after the video so that I can correct that, okay. So see, in this equation also you are getting the unknowns as c1 and c2, okay, all the other things are known. So let me number these equations as equation 4 and equation 5. Okay. So equation 4 and 5 are only having two unknowns, C1 and C2. So you have two unknowns, two equations. You can solve C1 and C2 and thus get the temperature profile. Okay. So this was one of the most complicated problem in one dimensional steady state heat transfer, just because you have taken the most complicated boundary condition, that is the mixed boundary condition in both the walls. Okay. And so in GATE you maybe you may have seen the temperature profile for steady state one dimensional heat conduction with uniform heat generation rate with Dirichlet boundary conditions at both the wall. Okay. So now if you have already forgotten that how that comes, then you must uh, derive that by yourself. So everything will be same. This will be the same governing equation for that case also, but there the boundary conditions will be just at x equal to minus L there will be some given temperature, at x equal to plus L there will be some given temperature. Similarly, if you are given the heat flux or if you are given the boundary condition that the wall is insulated, then the heat flux is given, that is 0. That is the Neumann boundary condition. So your homework is to play with this defined boundary conditions, okay, and uh, derive all the temperature profiles. So now what we will do is we will uh, see thermal networks. Okay, we will see thermal networks. So what do we mean by thermal networks? This also you have done in your B.Tech if you have done your heat transfer course. Okay, thermal networks means if you have a situation like, so this is one block and sorry and this is one block and these two blocks are joined. This block is having length, okay, this block is having length as L1, thermal conductivity as K1, okay, and cross sectional area is same for both the block A, and this block is having K2 A, okay, and the length is L2, okay. So now if you are given this problem, that maybe you are now given the Dirichlet boundary condition, that is in this phase you have temperature T1 and in this phase you have T2 that is greater than T1, then find the temperature profile. Okay, so if you are given this problem, then how can you solve? So first of all, you see that for a simple block, okay, if I had taken a simple just one block having Ka and L, okay, and here it is T1, it is T2, now T2 is less than T1. We will see that our Q dot is equal to Ka T1 minus T2 by L, right, and this we can write as T1 minus T2 L by Ka. Now don't ask me that how did you get this. If you are not getting this, then you can always derive this from the governing equation from scratch. Okay, so there is no heat generation, it is one dimensional, it is steady state, and with Dirichlet boundary conditions in both walls. Okay, now you see this I can write as delta T, that is equal to T1 minus T2 here, is equal to Q into L by Ka. So this is analogous to the formula delta V equals to I into R. So taking this electrical analogy, this heat flow is analogous to current. This L by Ka is called thermal resistance, analogous to electrical resistance, and temperature difference is analogous to the voltage difference. So these things I am covering because if there is anyone who is totally trusting on me for conduction heat transfer, if he is totally trusting on me that I will just watch these videos and then I will go to my GATE exam or my semester exam. So keeping that in mind, I will cover all the basics of B.Tech and also some more advanced level concepts. Okay, but obviously I will not derive everything, because the main objective in this course is not to give you each and every formula, but to make you able to derive each and every formula. Okay, so that means this L by Ka, this L by Ka is equal to RTH, and it is called as thermal resistance. Okay. Now the expression of this thermal resistance changes with the change in choice of coordinate system. If I write this thermal resistance in spherical or cylindrical coordinate system, then the expression will change, and I will derive in detail the heat conduction equation in cylindrical and spherical coordinate system. Okay, maybe in this video or in the later video. Okay, so if you are given this kind of a problem, so let me copy the schematic. Okay, okay, so this is the, so firstly let me choose a coordinate system. So here my coordinate system will be this is x and this is my origin. Okay, okay, so now if I solve this, then here I will get some temperature T, and this is unknown. Okay, this temperature is unknown, right? So now if I write the governing equation for block 1 and also for block 2, there will be the same governing equation. So the governing equation GE is d2x, sorry, d2t by dx2 is equal to 0. Okay, and that means my dt dx is equal to constant and my t is equal to cx plus c1, right? Now at x equal to 0, my t is equal to t1. So that means I can write my t1 is equal to c1, correct? Okay. Okay, so that is correct, right? Okay. Now I can also write at x equal to L1 I have some temperature, that is I am now writing as T star. Okay, I don't know T star, but I will find that. Okay, but in terms of T star, if I write the equation maybe A, I am labeling this as A. Okay, so then this will be C into L1 plus C1 is T1. So my C is T star minus T1 by L1, right? That means my dt dx all over the block 1 is equal to T star minus T1 minus L by L1. Keep this equation in your mind. I am labeling this as 1. So similar analysis if I do for block 2, then I will get, so let us do it again. This is 0 for block 2. So dt dx, now this is m1, another constant, and t will be m1x plus m2. Okay. Similarly, at x equal to L1 plus L2, my t is equal to T2, right? So T2 is equal to M1 into L1 plus L2 plus M2, right? And at x equal to L1, I have my T is equal to T star, right? Therefore, if I put this condition into this equation, it is B. Okay, so T star is equal to M1 L1 plus M2. So from these two equations, this and this, let us find the value of M1 and M2, right? So T2 is equal to M1 L1 plus M2, right, plus M1 L2. So this I have written from this equation, clear? And T star is equal to M1 L1 plus M2. So I can put this value of T star here. Okay, so that will be T2 is equal to T star plus M1 L2. That means my M1 is equal to T2 minus T star by L2. Okay, and that is nothing but my d2 dx for x greater than L1 and less than equal to L2. Okay, and this here, this equation is valid for x greater than 0 equal to L1. Okay, this L1 is L1 plus L2. Okay, right? Okay. Now you see that if I have to write the heat flux at the interface, okay, so at interface, that is at x equal to L1, I have my k minus k1 dt dx, okay, for block A at x equal to L1 is equal to minus k2 dt dx. Okay, so let me write it as T subscript A, that is the temperature profile for block A, and block B at x equal to L1 it is also. So then I can write my k1, now dTA dx is what? It will be this T star minus T1 by L1. right. So this will be T star minus T1 by L1, and this will be equal to K2. Now dTB dx, this will be this one, right, that is T2 minus T star by L2, okay. And actually basically if I put the minus here for both the signs, I am not cancelling the minus, and now I am writing K1 into, okay, K1 into T1 minus this one is equal to K2 into T star minus T2 by L2, okay. Because see that I have already assumed that my T1 is less than, sorry, T2 is greater than T1, right. I have assumed this T2 is greater than T1, okay. So that does not matter if you write this or this, I mean it is the same expression mathematically, this or this equation or this equation, both are same. But the main argument here is, you see that I think I have missed something, okay, I have not missed something, I mean, okay. So if I now multiply the area, okay, K2A, because the area is same for both, okay. So that will be, now I can write L by K1A is equal to T star minus T2 L2 by K2A, okay. Now you see that means the taking the analogy with the electrical network, the voltage difference by the RTH1, the thermal resistance 1, is equal to the voltage difference 2 by the resistance 2, okay. That is, if the blocks are in series combination, then the same heat flow will be there, because at any cross section, if that is in the steady state, okay, there should be a steady heat flow, and if a steady heat flow is there, then the temperature difference of block 1 by the thermal resistance of block 1 is equal to temperature difference of block 2 by the thermal resistance of block 2, okay. Therefore, the main objective of doing all these things were, if you have a block like this, okay, L1 K1 A1, L2 K2 A2, okay, then it is analogous to, okay, so let me draw it neatly, okay. So then it is analogous to sorry, this is my scenario, okay, and this is, I have L1 K1 A1 L2 K2 A2, okay. So and I have here T1 and T2 temperatures. This is analogous to, if I draw an electrical network like this, so here the voltage is T1, this voltage is T2, and here I have, this is resistance as L1 by Ka1, L2 by Ka2, okay. Then you can put this resistance as, if this R1 and R2, R1 plus R2, So the main crux of the matter is the the thermal network is equivalent to the electrical network. So you can do all the analysis with the thermal resistance that you have already done with your electrical resistances. That is, are if two blocks are in parallel in case of a thermal network, then you can convert that into a single block just by modifying the thermal resistances. And that you can do, that is, here the blocks are in series. So instead of that, if I had the situation like this, okay, so this is my block 1 and it is having T1 K1 A1 and it is having T2 K2 A2. Okay, so this is having thermal resistance R1 and this is having thermal resistance R2. Then the equivalent thermal resistance and having a block and having a single block here. Okay, so here this will have a thermal resistance of R1 R2 by R1 plus R2, right? It is the same analysis that you have already done with your electrical networks. Okay, so I will stop this lecture here. I have just proved that why the thermal network is equivalent to the electrical network, that we have got by just doing a simple case of two blocks in series. Okay, okay, so just before ending this lecture, let me tell you that how can you know that if the blocks are in parallel or series? If the temperature difference of for the two blocks are same, then then the blocks are in parallel, and if the temperature difference are not same, then they are not parallel. Okay, so this electrical network analogy is used in thermal and fluids engineering uh, very much, substantially. Not only in this thermal network analysis, but also in fluid also. Okay, during analyzing your pipe networks, you take up this analogy. Okay, there the voltage difference is analogous to the pressure difference. There is hydraulic resistance instead of thermal resistance or electrical resistance, and there is the fluid flow rate instead of current. Okay, so this analogy is very useful because we all have read this electrical network during our secondary and higher secondary studies, and we take that advantage in the higher level uh, courses. Okay, so we will take up the cylindrical and spherical coordinate analysis in the next lecture. Before that, you must have done your all the homeworks, and if you get any doubt and any difficulties, just put that in the comment box. And if you have any suggestion regarding my teaching, that if it is fast or slow or boring or anything, just frankly write that down in the comment box. According to that, I will try to improve myself. Okay, so until the next lecture, goodbye, take care, and thank you.